How computers understood humans. 10-slide introduction into deep learning and natural language processing of 2022. By his contrivance, the most ignorant person at a reasonable charge and with little bodily labor might write books in philosophy, poetry, politics, law, mathematics, and theology without the least assistance from genius or study. He then commanded 36 of his lads and read the several lines softly as they appeared upon the frame. From Gulliver's Travels by Jonathan Swift, 1726, making fun of Ramon, Llull, 1232. So the ideas of speaking computer, of computer capable of generating texts which are similar to books or as replies from humans existed at least since 1700s or 1200s. For example, this Ramon Llull written on this topic apparently extensively. He had these ideas of a graph of knowledge, alphabet of thought, and this idea of axioms that would generate rest of the ideas, which is very important because the knowledge is too large. We cannot express everything that we know that it's true. We need to have some kind of generative aspect, and we have a limited time. We cannot process everything. We need to understand in some abstract generative way from remembering just some basic attributes. And that's what we try to do in machine learning and natural language processing. So the ideas existed, but there wasn't enough compute, there wasn't enough understanding of computer science, not enough experience. The first question we will go through is how to instruct the computer to perform tasks, how to represent knowledge in computers, and how to generate the answers, how to generate thought inside of a computer. Okay, so let's continue. By the way, I have this at this website. You can get all the links there. You can subscribe as well on YouTube, on LinkedIn, on Twitter, by email. Yeah, subscribe by email. That's great. I can send you a newsletter, and you can also ask me. And yes, you can give some donation or subscribe by RSS or whatever. Okay, so yeah, I hope we will see you in future as well. So the next slide is then prompt as an interface. So in Odyssey 2001, they have this great idea of actually conversing with a computer in a plain manner. Basically, that means textual instructions. For example, I would, hey computer, explain this riddle to me, and I expect that the computer will generate answer text, and the answer text can be unspecified length. I cannot say ahead of time how much. I can sort of limit the maximum size, yes. So this input text, output text, super general interface, that's what's being used actually presently. So how would we like to represent knowledge in computers? How can we do this? So the first idea was to do something similar that we did with the books. So we had libraries. Those are textual documents that we can store in database. And in 1970s and 1980s, we started to have an ability to actually query by list of words. And by 1980s also to find topics in books. How we started doing that? So we basically used, we counted occurrences of words on the document level, stored them in sparse matrices. You can read more about space matrices here in this post. And by counting the words, so we created these matrices where we had words by documents, how many times the word appeared in the document, and we calculated these metrics like TF-IDF and latent semantic analysis. TF-IDF, it's very simple to explain, is that basically for each word in the query, we sum up, we are trying to create rank and sort documents that may be relevant, that contain at least one word from the query. And to do this, we sum for each query word, we sum some kind of rank how the document is correspond to that word and how the word is selective. And exactly like this, this IDF term operates, serves as a, it tells us how the word is actually selective, how it speaks, how much sort of information it gives us about some documents. For example, the word "the" appears very often times, or word "a", but it actually has no specific meaning. It does not select any specific document. It's not topic concrete. So that in that case, the weight of that query word would be very low. And at the same time, we then so this is sort of like information of the query word as for selecting the documents, and how much the document is about actually the query word. Latent semantic analysis, we can use this TF-IDF stored in a matrix, and we can then sort of diagonalize this matrix. We can sort of cluster the vectors of the matrix, and then we can, in this primitive manner, we can find topics stored in the document, in the database. So this is the most basic way how we can represent knowledge. But can we do better? Can we do better? So we can move from document level to sentence level. Once we have enough compute, we can start running more complicated algorithms like this. And at first, let's start with just a window of 10 words. What we can do here? Now, as we discussed with these matrices, and I would like to just define a quick term. If you are not familiar with vector, is a point in multi-dimensional space. It's basically an array of numbers. And age, and this is a vector. Okay, and so let's define this window of 10 surrounding words, and we move with this window across the document. And what we can do now is that we can count how often some words occur to each other. Okay, so let's create a vocabulary of 10,000 words and then count how they often appear close to other. And we can let's select the dimensionality of the space about 300. Okay, what we can do with this? Well, actually, dimensionality of 300 is much less than 10,000. That means that the vectors will suddenly become to be sort of like close together. There's not enough space for everyone to just go anywhere. They sort of start to have to fit somewhere close together. If we want to represent these words in these 300 dimensions, they cannot escape too much. It starts to suddenly push similar words close together. How can we do this? How can we push similar words together? Well, we can actually define this sort of global non-contextual word vectors. Yes, we will not have this disambiguation that flowering, which can mean fruit, or the fruit can mean flowering or a food. So we will not have this disambiguation. It will be global vector, but still can be similar. Interesting. Can we do this? How can we do this? So okay, you can, for example, here on this visualization we get three dimensions, and in the 3 dimensions we have visualized words that are sort of this is just a visualization of a result in 3 dimensions of this method called word2vec, which is a method how we can get these global vectors for words. How can we do this? So we can simply count co-occurrence of those 10 word windows. So we slide across the text, count co-occurrences, and then use that, then contract this 10,000 by 10,000 matrix into 300 dimensions and get vectors. That's called graph method. There's also this word2vec method, which gives you very similar results, slightly different. Again, we use surrounding 10 words context, but instead it is a training method which uses gradient-based learning. So how can we do this, right? We have this 10 sliding window and we want to create some sort of small problem, and then over time learn to do this correctly directly in the 300 dimensions. We don't want to create this huge matrix 10,000 by 10,000. How to do this? Well, easy. Yes, so how can we do this? So we can do this by saying words that appear in a similar context should be close in this 300 dimensional space. So we would like to take this input text. We have this window here, it's a window of 5, and we'd like to predict the middle word. What can be in the middle? The text says, "This truth I, therefore I am." What is in the middle? In the middle there's a word think. How can we get it? We take the word vectors that are initialized somehow, we sum them up, and then we look up resulting vector, and we require it, we train it to be close to a context vector. This is how the word2vec method works. It requires less memory. Okay, so how let's continue. Knowledge graphs. So the issue there in the word2vec is that we did the sliding windows. We can predict the middle words. We have vectors for each word in 300 dimensional space. But the issue here is that these are global vectors. But instead, how we can imagine storing human knowledge is as if in this knowledge graph. Actually, let me switch. Knowledge graph is are these connected nodes with directional arrows, and I refreshed just to have my domain over here, not localhost. So knowledge graphs are is these graphs that are connected, and each node can represent one unique word, and we can connect these words and sort of say something about them. And in this way we can represent information, and it's completely contextualized, because for apple and for others, for fruit as a food, we can have one node, and for fruit as a flowering, we can have another word, and so these words are disambiguated. So this is like a Wikipedia. And Wikipedia, you have these pages, right? Or on internet, you have web pages, and these are unique. They can link to each other, say how they are related to each other, but they are unique even though they may have maybe similar titles, but they have different domains. The domains are unique, but the titles can be the same, right? You can have fruit web page on one domain, fruit web page on. Okay, so we can disambiguate in this way, in this kind of structure. And as well, walking across this knowledge graph, so I have this apple is a subclass of fruit, and fruit has as a subclass a pear. Pear has a color red, and red is also a color of apple, and apple has color of yellow as well. And I can ask, can yellow be color of pear as well when both are fruit? Yeah. So as you noticed, I walked across the knowledge graph. I was sort of generating sentences, right? That's something like with the text. Like text, human text, is something like walking randomly across this vast implicit knowledge graph, this sort of infinite knowledge graph, where each word is fully contextualized within the text. And yes, maybe there's let's make an decision that each word can be fully contextualized, that there's no like explicit fuzziness, that we can, you know, that of course everybody can define their words as on their own, but in that case we can then just create a separate node for them in the knowledge graph, right? And so this knowledge graph sort of represents generated text, and in this case then we can ask, can we actually predict that once we are walking across this graph, that we can actually travel from yellow to pear through verb has a color. This is called link prediction, and it's sort of like generating text. So this is what I wanted to say. It's important for then to understanding the contextualized vector words. So this abstraction, this ability to predict links, actually, and we can see that the knowledge graphs are sort of related to sentences, and we can use similar methods to create embeddings for. But this abstraction, for that, we need to some kind of way how to contextualize vectors in this abstractive way. So for that, currently we use this model called transformer, where the word meaning is based on a context of surrounding 100 words. With that, the closer the words are, the more sort of have implicit bias to be influenced by each other, but it's not bulletproof. Words far away from each other can influence each other. And how it works, that this transformer is layered. So we input something like word2vec. Yeah, we have vectors for each word. We input that. Then we have some kind of layered architecture, which increases sort of abstraction. It sort of mixes the words together, and that one then outputs. Then we get an output from the transformer of contextualized word vectors, which then similarly as the word2vec also can predict missing words, hidden words. So this is called transformer architecture. There are other architectures that were successful in the past, like LSTM. Those are recurrent neural networks. So instead of passing everything at once, we can instead pass it repeatedly in sequence to the model, and the model needs to sort of approach it sequentially with memory. It needs to remember what it saw. And I have specific post about special architecture like this. You can click here, or you can read more about transformer clicking here. And so this architecture, by having this layered and accepting everything at once, can contextualize words and sort of point to the right place in the knowledge graph, right? And so right now we are at the point in 2020 that we have these huge transformer models that cost $10 million, are trained on large amount of text that would take many human lives to read. That is primarily created from the internet, which is the biggest source of information at the moment. And these models now can generate text abstractively. It can fulfill simple tasks. It can simulate human thinking, sometimes with human level performance. And the results are amazing. How those work, they also use basically transformer architecture that was mentioned previously. It is slightly different setup in that it predicts only the next word and only looks at the past tokens, but it's essentially it's still transformer architecture. And the latest one, as of time of this video, is this pathways language model, for which you can read more or watch video right here. And that's all. That's the introduction. You can subscribe by mail to my newsletter. I encourage specifically that because we can, in distributed manner, communicate. Or you can subscribe Twitter, YouTube, LinkedIn, GitHub, Facebook, RSS, and you can ask a question clicking this button or this button, or on Twitter. And with that, thank you very much, and hope to see you next time. Bye.